Welcome to Topic 3, To Infinity and Beyond, the Flight Environment. In the next two videos, we are going to talk about this atmosphere around Earth and the exoatmosphere around Earth. In video 1, we will talk about the basic atmosphere, both near and far, and in video 2, we'll talk about the standard atmosphere. Additionally, there are slides and additional material on the determination and calculation of properties of the atmosphere that you can look at. Understanding only German, Fritz was unaware that the clouds were becoming threatening. Think about that. Are clouds a standard or non-standard feature of the atmosphere and what that means? And then, what happens when the atmosphere interacts with the ground? Thinking about a mountain goat in a cloud bank, or as my father called it when he was flying, a cumulogranite cloud. So, questions for today. What is the atmosphere? What do we mean by the atmosphere, especially in the context of aerospace engineering? What is the lower atmosphere versus the upper and exoatmosphere? How do the properties of the atmosphere affect our aerospace vehicles? And how do they affect how we design our aerospace vehicles, how we operate them, and ultimately how we communicate with them, because that's an important construct. Also, you need to be able to, or think about how you differentiate between the homo and heterospheres, and we'll talk a bit more about that. So, if you're doing additional reading, please check Anderson chapter 3 about the atmosphere. Okay, so our goals. In this, we're going to develop an understanding of Earth's atmosphere, the properties, temperature, pressure, density, the effect these properties have on aircraft. And we'll talk about that a lot more through the remainder of this unit, especially when we get to flight mechanics and performance. And then we're going to give you a little introduction to the standard atmosphere. And then we'll ultimately be able to help you working through questions of how you calculate different properties in the standard atmosphere. So our atmosphere, let's introduce it. We have the vertical structure of our atmosphere here. It is made up into two primary layers, the homosphere and the heterosphere. And as you'll see, they break roughly around 100 kilometers in altitude. And that's very meaningful. Think about in popular or more popular reasonings, what happens at 100 kilometers, what we consider the difference between below 100 kilometers and above 100 kilometers. We can further break up the heterosphere and the homosphere into further sublayers. And we have the bottom, the troposphere, followed by the stratosphere, the mesosphere, and the thermosphere. Everything above the thermosphere is the exosphere. In this region of the mesosphere and the thermosphere, we have the ionosphere. Below that, the ozonosphere. And this talks about, each of these talk about different properties of the atmosphere. So what do we mean by homosphere? And what do we mean by heterosphere? Well, homo comes from the Greek word meaning the same, and hetero from the Greek word meaning different. What it means is that in the homosphere, we can treat the atmosphere as if it's made up of a single gas, be that oxygen or nitrogen or the like. In fact, it's an average of the makeup of gases. So we're talking 78% nitrogen, 21% oxygen, and 1% remainder. However, when we get to the heterosphere, we can't do that. The gases are rarefied enough that we have to treat each gas as its constituent part. And it is a statistical operation that we need to do. Ozonosphere just means that's where most of the ozone relies. The ionosphere, it's an ionized bit of gas, and that's very important for communication. And then the exosphere, we're talking about an area where the interaction between an aerospace vehicle and the atmosphere is relatively small. And so we don't have lots of what we would call drag, but we might have lots of other behaviors. And if you're familiar with the Discoverer program here at the university, you will know that that is designed to work in the exosphere and the upper ionosphere. Okay, so let's start with the lower atmosphere. In the lower atmosphere, that first layer is the troposphere. And troposphere comes from the Greek for mixing. It's the mixing part of the atmosphere. And because it mixes, it has a phenomenon we call weather. And weather, without mixing, you just don't get weather. As a consequence of this, it also has the vast majority of the water vapor. And we'll talk about what that means. But it means this is where the clouds typically rely. As we go up in altitude, our standard properties, temperature, pressure, density, humidity, all of those things decrease with altitude. We have less temperature as we go up. We have less pressure. Pressure always decreases with altitude. It's a physical property of the mass above you. And consequently, because air is a compressible fluid, we have less density. As the pressure and temperature go down, we can contain in it less water, so our humidity goes down. Now, we're going to talk about, when we get to the standard atmosphere, the quote-unquote thickness of the troposphere. But one of the things I want you to remember is that the thickness depends on the time of year and the location where you're at. So the troposphere is thickest at the equator and thinnest at the poles. And so what happens is we get a lot more weather at the equator than we do at the poles, a lot more mixing. And that makes a big difference for what happens in a lot of our climate and weather phenomena, but it also makes a difference for how you fly an aircraft. Flying an aircraft around the poles is different than flying an aircraft to the equator. And we have to take that into account when we do route planning. But for now, we're just going to assume it's a constant layer. Above the troposphere, we have the stratosphere. And for most of our aeronautical craft, it's these two layers that we care about. Stratos comes from the Greek word for layered, so stratified rock, for instance. And then we break it up into two sublayers. So we have a layered layer broken up into further layers. And the upper and lower is what we call those. And the reason we break it up into two sublayers is the properties of the atmosphere change slightly between the two. Now, one of the things about the stratosphere being layered, it means that anything you leave at an altitude in the stratosphere tends to stay there. So if you put any water vapor in there, it stays there. It's also why we get cirrus clouds, those really high, thin clouds that you see on a nice day. Those are in the stratosphere. But because they stay in a layer, they spread out laterally, but they don't move up and down like a cumulus or a stratus cloud. In the lower stratosphere, the temperature is typically regarded as constant. That means it doesn't change with altitude. That means properties like speed of sound remain essentially the same as you go up there. One of the interesting things is we get to the upper stratosphere, the temperature starts to increase with altitude. And this is because we're getting a lot more radiation from the sun that excites the atmosphere. At the lower ones, the insulation of the atmosphere is sufficient to prevent that from happening. As always, pressure continues to decrease. And as we said, very little mixing occurs. And this is going to be very important when you start thinking about climate effects. Because while CO2 is the best known of greenhouse gases or global warming gases, water is very strong, in fact, significantly stronger than CO2 greenhouse gas. In the troposphere, where we have lots of mixing, it's not a problem. Water doesn't stay in the atmosphere very long. But in the stratosphere, that equation changes. One of the other things about the stratosphere is the thickness varies a lot less. The upper stratosphere doesn't change that much. It's really only the lower stratosphere where it mixes with the troposphere, where that interface that changes with location and time of year. Okay, so we just talked about that point where the stratosphere and the troposphere meet. We call that the tropopause, the boundary, the pause of mixing. And it is literally the point at which substantial mixing stops in the atmosphere. In our standard atmosphere, which we'll talk more about in the second video, this is said to occur at 11,000 meters or 36,100 feet. And what this means is that we consider these two atmospheres as breaking, as behaving differently. And when we talk about the equations for the standard atmosphere, they will break. They will have hard corners. They will not be smooth across this point. Again, because the thickness of the troposphere varies with location and time of year, the tropopause location will vary with time of year and latitude. It also varies with temperature on the day, not as much as location and general time of year, but time of just look temperature on the day. As we said, most weather occurs below the tropopause, and that's because we require mixing to have weather. Okay, we've talked a little bit about the lower atmosphere, and hopefully you're a little bit more familiar with it. And obviously, if you keep this in your mind as we start talking about more performance and other things about aerospace vehicles in the future topics, it'll help you. Let's talk a little bit more about the upper atmosphere, those areas above the stratosphere. We're talking about the mesosphere and the exosphere and the heterosphere and the like. Again, coming back to this, we're going above the stratopause. We have the mesosphere and the thermosphere, our standard with the mesopause and thermopause. And here we see we are now working in the higher homosphere and into the heterosphere. So this is not something, if you're working on an aeronautical vehicle, you'll deal with a whole lot. It is a thing if you're working on spacecraft, launch vehicles, reentry vehicles, very low Earth orbit vehicles, and even mid-Earth orbit, low and mid-Earth orbit vehicles, you're going to need to consider in your design and your operational considerations. So, first question, is there an atmosphere in space? And put it simply, there is. Absolutely. There is an atmosphere basically anywhere you are around Earth. Now, obviously, as you get further and further away from Earth, the effect of that atmosphere gets less and less. It typically consists of the thermosphere and the exosphere. It is a heterosphere. Because of this, you cannot use something called continuum mechanics. So in fluid dynamics right now, you are doing continuum mechanics. The momentum equation, the continuity equation, Bernoulli, all of those things. The definition of dynamic pressure, all of that fall apart. You can't use the hydrostatic equation anymore. No longer do you have enough matter above you to calculate the local pressure. And then finally, in the thermo and exosphere, because we're now in the ionosphere and above, we have lots and lots of charged particles. Now think about what that means. Obviously, it causes havoc with electromagnetic waves because charged particles can change and bend those waves as they go through space, or the atmosphere in this case. It also means that we have lots and lots of particles that want to react with other particles. And those particles are likely to be your vehicle. So this means materials degrade much faster in the thermosphere and the exosphere than they do at lower altitude. In fact, that's one of the problems that we're researching in the Discoverer program, is how you deal with the fact that your materials react to atomic oxygen very, very quickly. Okay, that's going to conclude our discussion in this video, part 1 of topic 3. In the next video, part 2, we're going to talk about the standard atmosphere. So what we've talked about so far are the general properties of the atmosphere and how they vary in different changes. The standard atmosphere is meant to create something that we as aerospace engineers can use, especially for design, but also for operations, and that we can deviate from in a very consistent and reliable manner. So I hope you stay tuned and join me.